Okay, let's dive in. We are talking today about a scientist who, well, Albert Einstein himself said marked a fundamental shift in science.
Yeah, Einstein's quote is pretty powerful, isn't it? That James Clerk Maxwell's work effectively closed one scientific era and opened up a completely new one.
It's incredible praise. I mean, that puts Maxwell right up there with Newton and Einstein. That's the top tier.
It's totally deserved, I think. We talk about the big unifications in physics, Newton bringing together heavens and earth, Einstein linking space and time. But Maxwell, he pulled off the first huge theoretical unification.
Electricity, magnetism, and light, all wrapped up together.
Exactly, into one sort of beautiful mathematical structure. It's the bedrock for, well, almost all our modern tech.
So our mission today for this deep dive is really to explore Maxwell's genius on two fronts. First, that massive achievement, unifying electromagnetism, the theory behind all things electric, all communication. And second, something maybe less talked about but just as revolutionary. His work pioneering statistical thinking, using probability in physics, a totally new way to handle systems with countless particles.
And here's the really mind-bending part we want to get across today. We're going to show you how Maxwell's equations, written back in the 1800s, were somehow, almost magically, future-proof.
Future-proof? How so?
They were already perfectly set up for 20th century physics. Special relativity, quantum mechanics, the deep mathematical structure Maxwell built, had the right symmetries, the right features, baked right in, decades early.
Wow, it's like he designed a key without even knowing what locks it would eventually open. Okay, so where do we start? Maybe with that less famous revolution, the jump into probability?
Yeah, let's do that. Because while the field equations get the headlines, his shift towards probabilistic physics, what became statistical mechanics, was just as radical. And it actually started, believe it or not, by looking at outer space.
Saturn's rings, right. I remember reading that this early work was key to his later ideas about statistics.
Absolutely. Back in the 1850s, nobody really knew what Saturn's rings were. Solid, liquid. It was a big mystery.
And Maxwell tackled it mathematically.
He did. Using some really clever modeling, he proved that the rings couldn't possibly be a single solid structure, or even a fluid one. Gravity would just rip them apart.
So his math forced the conclusion
That they had to be made of, as he put it, innumerable small particles, like a huge swarm of tiny moons, each orbiting independently, colliding, interacting.
Okay, so dealing with this vast number of separate things, that kind of set the stage.
It really did. It showed he could think about systems with immense numbers of components in motion, and that naturally led him to think about gases. Because what's a gas, really?
Just a massive collection of particles bouncing around.
Exactly. Billions upon billions of them.
And this is where he breaks from the old way of doing physics, the Newtonian way.
Totally. Newton's physics was deterministic. If you knew the exact position and velocity of every single particle at the start, you could theoretically predict the entire future of the system.
Like clockwork.
Right. But try doing that for the air in this room. There's something like, 10 to the power of 19 molecules in just a tiny cubic centimeter.
Forget it. Impossible to track individually.
Not just impossible practically, but maybe even conceptually the wrong way to think about it. How do you describe something that complex?
And this is where Maxwell, along with Ludwig Boltzmann, comes up with this radical idea. Stop trying to track individuals. Use statistics instead.
That's the big leap. It's a philosophical shift, really. Instead of asking, where's particle number 53 billion right now? You ask, what's the probability that any random particle has a speed in this particular range?
So you lose the detail about individuals.
But you gain certainty about the whole group. You can make incredibly precise predictions about the gas as a whole, even though you know almost nothing about any single molecule within it.
Trading impossible precision for predictable averages. And that leads to the Maxwell-Boltzmann distribution.
The cornerstone, yeah. It's a specific mathematical formula, a probability distribution, that tells you exactly how the speeds of particles are distributed in a gas, if that gas is in thermodynamic equilibrium.
Thermodynamic equilibrium, what does that mean in simple terms?
It basically means the gases settle down. Macroscopically, its temperature, its pressure, they're stable and the same everywhere throughout the container. The individual molecules are still whizzing around, crashing into each other, changing speeds constantly.
But the overall picture stays the same.
Exactly. The distribution of speeds, how many are going fast, how many slow, how many medium, that pattern remains constant. It's a dynamic balance.
And the graph of this distribution, it's not symmetrical like a bell curve, is it?
No, that's a key point. It starts at zero speed, got to be moving somehow, then a piece at the most probable speed, And then it has this long tail stretching out towards higher speeds.
And that tail is important.
Very important. That tail represents the small fraction of molecules that happen to have much higher energy, much higher speed than the average. It's why water evaporates even when it's not boiling. A few energetic molecules have enough speed to break free from the surface.
And this isn't just abstract theory. You can use this formula to calculate real things.
Oh, absolutely. You can take the Maxwell-Boltzmann formula, plug in the temperature and the mass of the gas particles, and calculate actual speeds, like nitrogen, the main component of air.
What's its speed at room temperature?
At about 300 Kelvin, typical room temp, the most probable speed for a nitrogen molecule comes out to roughly 422 meters per second.
Wow. Faster than sound.
Yep. It shows how this abstract statistical idea connects directly to measurable reality. It's powerful stuff.
So he's created this whole new statistical way of looking at physics, but then, typical Maxwell, he immediately starts pushing its limits, right? Testing the boundaries.
Which leads us straight to Maxwell's demon, probably his most famous thought experiment. It was his way of really probing the second law of thermodynamics.
The entropy law. The idea that disorder or entropy in an isolated system always tends to increase. Things run down, they don't spontaneously tidy themselves up.
Right. Disorder wins in the long run. But Maxwell cooked up this scenario. Imagine a tiny, intelligent being, the demon, sitting at a tiny door between two chambers filled with gas, both initially at the same temperature.
And this demon can see individual molecules coming.
Yeah, it can see how fast each molecule is moving. And it operates this tiny frictionless door. Its job.
To sort them. Let the fast ones go one way, the slow ones the other.
Exactly. It opens the door just long enough to let a fast molecule from chamber B into chamber A, and a slow one from A into B. Over time, chamber A gets hotter, full of fast molecules, and chamber B gets colder, full of slow ones.
Uh-oh. So you've created a temperature difference, reduced the overall entropy, seemingly without doing any work. That looks like it violates the second law, like getting free energy.
It absolutely looked that way. This little thought experiment caused headaches for physicists for like 70 years. Does the second law have loopholes? Is it just statistical, meaning it can be violated by something smart enough like the demon?
So how did they eventually solve the paradox? It wasn't about the sorting itself, was it?
No, the breakthrough came from realizing the demon needs information. People like Leo Szilard, later Rolf Landauer, they figured it out. To do the sorting, the demon has to measure the molecule's speed, store that information, make a decision.
Okay.
And to keep doing this indefinitely, the demon eventually has to erase its memory to make room for new measurements. And Landauer's principle showed that the very act of erasing information, physically resetting a memory bit, must generate a minimum amount of heat. It must increase entropy somewhere.
So the entropy increase from erasing the demon's memory always cancels out or even outweighs the entropy decrease from sorting the molecules.
Precisely. The second law holds. But the amazing takeaway is this deep link Maxwell stumbled upon between thermodynamics and information. He basically launched the field of physics of computation by accident in 1871. It just shows his incredible depth. He wasn't just solving problems, he was finding connections no one else saw.
That ability to see connections, to think conceptually differently, seems key to his other great work, to electromagnetism. But that story involves another giant, Michael Faraday, who worked in a completely different way.
Oh, the Maxwell-Faraday relationship is just fascinating. Faraday was this brilliant experimentalist, largely self-taught, not really a mathematician in the formal sense. He visualized physics.
Those famous lines of force filling space around magnets and charges, like invisible pathways.
Exactly. He had this holistic picture of the field and described its behavior through experiments. But mathematically trained physicists at the time struggled with it. It seemed kind of hand-wavy. They liked calculating forces between points.
So Faraday had the vision, but not the mathematical language.
Right. And Maxwell saw this. He saw the power in Faraday's field concept, this idea that the space between charges wasn't empty, but filled with this physically real field-carrying energy. Maxwell realized the standard mathematical tools weren't up to the job of describing Faraday's vision.
So what did he do?
He made a really deliberate choice. He said, essentially, I need to stop thinking like a traditional mathematician for a moment and really get inside Faraday's head. I need to understand his lines of force first before trying to write equations.
So the math genius had to learn to think visually, like the experimentalist.
Yes. And that willingness to embrace a different way of thinking was crucial. It pushed him to develop new mathematical tools like vector calculus concepts to properly translate Faraday's field lines into a rigorous theory. It's a perfect example of genius building upon genius.
Okay, so he takes Faraday's intuitive picture and sets out to build the mathematical engine for it, which brings us to the magnum opus, the unification of electromagnetism.
And when we learn about it now, we see these four neat, elegant equations. Gauss's law, Faraday's law, Ampere's law with Maxwell's addition, and the one about magnetic monopoles.
Yeah, the Maxwell's equations we see in textbooks.
But historically, it didn't just pop out like that. It was a much messier process. Maxwell's big paper in 1865, A Dynamical Theory of the Electromagnetic Field, didn't have four equations.
How many did it have?
It presented the theory as a system of 20 equations relating 20 different variables.
20. Okay, that's definitely not the streamlined version. Why so many?
Well, he was still working within the context of the time. Physics then was obsessed with the idea of the ether, this invisible substance filling all of space that light waves supposedly traveled through.
Like an invisible jelly?
Sort of, yeah. And in his earlier work, Maxwell actually used these elaborate mechanical models like spinning vortices in the ether, tiny idle wheels acting as ball bearings between them, as a way to try and visualize and calculate how electromagnetic effects might propagate.
So the equations had to describe all that mechanical scaffolding, too?
Initially, yes. He had separate equations for electric displacement, magnetic force, currents, potentials, fields, all these different aspects treated somewhat separately. It was really only in the 1865 paper that he managed to mostly strip away the direct mechanical analogies and present it more purely mathematically, focusing on fields and potentials.
So who boiled it down from 20 to the 4 we know today?
That major simplification came later, mainly in the 1880s, thanks to Oliver Heaviside and Josiah Willard Gibbs. They were pioneers of vector calculus, and they realized they could use this new, more compact mathematical language to rewrite Maxwell's system much more efficiently.
So the Maxwell's equations we use are really the Maxwell-Heaviside-Gibbs equations.
In terms of notation, absolutely. And it's interesting because while Heaviside's vector form is super useful for classical problems, dealing just with the E and B fields we can measure, Maxwell's original formulation, with its heavy emphasis on the underlying potentials, things we call phi and A, actually turns out to be closer in a deep way to how we need to think about electromagnetism in quantum mechanics. We'll get to that later.
Okay, but back to the core breakthrough. The one piece Maxwell himself added that changed everything, the displacement current.
This is the crucial addition. He looked at Ampere's law, the rule describing how electric currents create magnetic fields, and he realized it was incomplete. He added this term, partial D director, the rate of change of electric displacement.
Why? What was broken without it?
The math just didn't work consistently, especially when he thought about charging a capacitor. Ampere's original law said magnetic fields only come from moving charges, actual currents flowing in wires.
Okay.
But think about a capacitor charging up. There's current flowing in the wires leading to the plates, but in the gap between the plates, where there's vacuum or an insulator, there's no actual charge moving across.
Right, it's a gap.
Yet, experiments clearly showed a magnetic field did exist around that gap while the capacitor was charging. Ampere's law, applied to a loop passing through the gap, predicted zero magnetic field because no current pierced the loop's surface. It failed.
And this wasn't just awkward, it broke something fundamental.
It broke charge conservation. The idea that charge can't just vanish into thin air. Maxwell saw that the changing electric field in the gap had to be doing the same job as the current in the wire. It had to be creating the magnetic field.
So the displacement current term fixed that inconsistency.
Perfectly. It restored charge conservation, and crucially, it introduced a beautiful symmetry. We already knew from Faraday that a changing magnetic field creates an electric field. Maxwell's term showed the reverse. A changing electric field creates a magnetic field.
They create each other, like a feedback loop.
Exactly. And that reciprocal relationship, that symmetry, is what allows electromagnetic disturbances to propagate. It's the engine for waves.
And once that symmetry was locked in, the equations basically screamed, waves!
They did. If you combine Faraday's law with the now complete Ampere-Maxwell law and do a bit of vector calculus, out pops a wave equation. The math predicted that these coupled electric and magnetic fields should travel through space as a self-sustaining wave.
An electromagnetic wave, predicted purely from theory. But the bombshell was the speed of this theoretical wave. How did he figure that out without actually seeing one?
This is the goosebump moment in physics history. The speed predicted by his wave equation depended only on two constants that were already known from completely separate, static electricity, and magnetism experiments.
Nothing to do with light or waves originally.
Nope, just numbers describing how strong electric forces are in a vacuum, epsilon dollars, the permittivity, and how strong magnetic forces are, the permeability. Maxwell plugged the measured values of these constants into his equation, 4 all squared on.
And the number that came out
Was around 310,000 kilometers per second, which was astonishingly close to the known speed of light measured by optical methods.
He must have known instantly.
The conclusion was inescapable. Light was this electromagnetic wave. Optics, electricity, magnetism, they weren't separate subjects anymore. They were different facets of the same underlying phenomenon. They're the greatest unifications ever.
Just stunning. And this wasn't just a calculation, it was later proven experimentally.
Oh, yes. Heinrich Hertz, in 1887, deliberately generated and detected radio waves in his lab, confirming Maxwell's prediction and kicking off the age of wireless communication.
Okay, so that's the 19th century triumph. But the story gets even wilder in the 20th century because it turns out Maxwell's equations were already speaking the language of relativity.
This is where Maxwell goes from genius to, like, Nostradamus of physics. See, classical Newtonian physics worked with Galilean relativity, just at velocities. If I throw a ball forward at 10 mile per hour from a train moving at 50 mile per hour, someone on the ground sees it moving at 60 mile per hour. Simple addition.
Makes sense.
But if you tried to apply that same logic to Maxwell's equations, they changed form. The equations describing electromagnetism looked different depending on how fast you were moving. This deeply bothered physicists.
It suggested there had to be one special, absolute frame of rest in the universe, the frame of the ether where the equations took their simplest form.
Exactly. And people like Michelson and Morley spent years trying to measure Earth's motion through this supposed ether. But they found nothing. Zilch. The speed of light seemed to be the same no matter how the Earth was moving.
So the experiments contradicted the simple velocity addition, but matched Maxwell's equations.
Precisely. The awkward truth was, Maxwell's equations weren't wrong. Our intuitive ideas about space, time, and velocity addition were. The equations already had a hidden symmetry called Lorentz invariance.
Lorentz invariance, meaning?
Meaning, the form of Maxwell's laws stays exactly the same for any observer moving at a constant velocity. If you and I are moving relative to each other, we'll measure different values for electric and magnetic fields sometimes. But the fundamental equations relating them remain identical for both of us. And crucially, we both must measure the same speed of light.
Two Cyriciles.
So Einstein didn't invent the constancy of the speed of light. It was already embedded in Maxwell's work. Essentially, yes. Einstein's genius was recognizing this, elevating it to a fundamental postulate of nature, and then figuring out how space and time themselves must transform between observers, the Lorentz transformations, to make Maxwell's equations invariant for everyone. Maxwell provided the relativistic template without even knowing it.
And the best way to see this pre-built relativistic structure is using the math tools of relativity itself, like 4 vectors.
Exactly. 4 vectors are the natural language of spacetime. Instead of treating time and space, 6 daggers y, z, as separate, you bundle them together into a single 4-component object. 6 mu nu equals ct x, y, z.
Why the c with time?
Multiplying time by c gives it units of distance, so all 4 components have the same dimension. It treats time as another coordinate on par with space.
And why is this bundling useful?
Because when you switch between moving observers using the correct Lorentz transformations, these 4 vectors transform in a very specific, elegant way that automatically preserves the underlying physics. Laws written using 4 vectors are automatically relativistic.
And there's a way to measure distance in this 4D spacetime that everyone agrees on.
Yes, that's the Lorentz invariant interval. It's like the space-time version of Pythagoras' theorem, but with a crucial minus sign. $2 ct2 by 2y 2z22. This value, the interval squared between 2 events, is the same for all inertial observers. It's a fundamental geometric property of spacetime.
So the math guarantees consistency across different viewpoints. And this doesn't just unify space and time, it unifies electrical concepts too.
It does. Take charge density, how much charge is packed into a volume, and current density, how much charge flows across an area per time. Classically, they seem distinct.
Yes, static charge versus moving charge.
But relativity shows they're 2 sides of the same coin. They combine into a single 4-vector current. Jimu mo. JBC, GX, shaker, shake.
Why do they have to combine?
Think about it. If you see a line of stationary charges, that's just charge density, the dollar.
Sure.
But if I fly past that line...
You see them moving, so you see a current.
Exactly. And not only that, because of Lorentz contraction, the spacing between the charges looks different to me, so the charge density A also changes. What one observer sees as pure charge density, another sees as a mix of charge density and current density. They have to be part of the same four-vector package to transform correctly.
Okay, that makes sense. And this simplifies basic laws, like charge conservation.
Dramatically.
Yeah.
The classical equation for charge conservation, the continuity equation, looks a bit clunky. But in four-vector notation, it becomes stunningly simple. Partial mu actually mean.
Partial mu represents the four-dimensional divergence. Summing over the index mu, which is called contraction, makes the whole thing a Lorentz scalar, a single number whose value is 0 in all reference frames. So writing it this way manifestly shows that charge conservation is a universally true law built into the relativistic structure. It just is 0 for everyone.
Wow. Okay, now for the really counterintuitive part. You're saying magnetism isn't really a separate force, it's just electricity viewed differently. Essentially, yes, it's a relativistic effect. Let's use the standard example, a current-carrying wire and a moving test charge.
Okay, so in the lab, the wire has electrons drifting one way, positive ions stationary. Overall, it's electrically neutral. We shoot a charge dollar parallel to it.
In the lab frame, there's no electric field from the neutral wire. But there is a magnetic field, $dollar, due to the current. So the moving charge feels a magnetic force. 2Q math BFU, dollar law. Standard stuff.
Now, jump into the shoes of the test charge. From its perspective, it's stationary.
Right. If it's stationary, the magnetic force, 2 math BFB, must be 0. But physics can't depend on who's looking, so there must still be a force somehow. What happens?
Well, from the charge's frame, the wire is moving past it, so the positive ions are moving backward.
And the electrons are moving backward too, but at a slightly different speed than the ions because of their original drift.
Ah, so the relative speeds are different now.
And because they're moving relative to the test charge, Lorentz contraction affects their spacing. And crucially, because the ions and electrons have different relative speeds in this frame, their densities change by different amounts.
Meaning the wire is no longer electrically neutral in this frame?
Exactly. Due purely to relativistic length contraction differences between the positive and negative charges, the wire appears to have a net electric charge density.
So it creates an electric field.
It creates an electric field, math BFE1, and this electric field exerts a purely electric force on our now stationary test charge. The magnetic force vanished, but an electric force appeared to take its place.
So the force we called magnetic in the lab frame is the electric force in the charge's moving frame.
Transform that electric force back to the lab frame, and you recover the magnetic part of the Lorentz force. Magnetism is fundamentally a relativistic consequence of electrostatics.
But wait, Lorentz contraction is usually tiny unless you're near light speed. Electron drift speeds in wires are incredibly slow. Why is magnetism such a strong, obvious force if it's just this tiny relativistic effect?
Fantastic question.
Oh.
It's because the underlying electric forces between the charges in the wire are enormously strong, like astronomically strong.
Okay.
Electrical neutrality in a wire means you have this colossal repulsion between electrons and colossal attraction between electrons and ions, balanced almost perfectly. Magnetism arises from the tiny relativistic imbalance due to the different contractions and those huge underlying forces. Because the net electric force is 0 in the lab frame, even this minuscule relativistic remainder shows up as a distinct, noticeable force, the one we call magnetic.
Mind blown. Okay, so E and D aren't independent. They must be parts of a bigger structure.
They have to be.
Yeah.
And that structure is the electromagnetic field tensor, A5. It's a 4x4 matrix.
Like a grid of numbers.
Yeah. And its components aren't just numbers. They are the components of the electric field, XAZ, XAZ, and the magnetic field, XD by V, arranged in a specific antisymmetric way.
And this tensor is the key.
It's the master object. When you apply a Lorentz transformation, representing a switch to a moving frame, to this single tensor, its components mix together exactly right so that what was purely electric field in one frame becomes a combination of electric and magnetic fields in another, perfectly matching special relativity. E and B rotate into each other within this tensor structure.
So the tensor captures the unified field. Does it simplify the force law too? That Q math BFE plus math BFB looked complicated.
It gets much cleaner. The relativistic force law, written using 4 vectors in the field tensor, is just BP mo tau Q F nu.
Okay, unpack P mu and tau.
P mu is the form momentum. Its time component is energy divided by c, and its space components are the regular momentum. Nu is the force velocity of the particle, and tau is the crucial bit. It's the derivative with respect to proper time.
Proper.
That's the time measured by a clock strapped to the particle itself. And the beauty is all observers, no matter how they're moving, agree on the proper time interval tau for the particle.
So because Rman is a tensor and Luhmann transform correctly, the whole equation holds true for everyone. The physics is the same.
That's the elegance of the covariant formulation. It guarantees relativistic consistency.
Now, even though E and B themselves change between frames, are there things about the field that don't change, things everyone agrees on?
Yes, there are two combinations of E and B that are Lorentz invariant scalars. Everyone calculates the same value for them.
What are they?
The first one is 22D B22, actually 22C2 B22 if using standard units. The second is E2$B, the dot product.
What does E2B22 tell you?
It tells you about the fundamental nature of the field region. If E2B2, it means there's some reference frame where the magnetic field vanishes entirely and it's a purely electric field. If E2D2, there's a frame where the electric field vanishes and it's purely magnetic.
And if it's 0?
If E2B equals a Fort line, it means the magnitudes are related by E equals CB all. That's the condition for a pure electromagnetic wave, like light traveling in a vacuum. That condition holds in all frames.
And the other invariant, Umia-Dalbade.
If U.B equals a lol dollar, it means the electric and magnetic fields are perpendicular, like in a simple light wave. And if they are perpendicular in one frame, they are perpendicular in all frames. If U.B is not 0, it means the fields have parallel components, and that property also persists across frames. These invariants reveal the intrinsic character of the electromagnetic field, independent of the observer's motion.
So Maxwell built something that already had the geometry of space-time woven into it, which leads us to its modern legacy, quantum theory, energy, even cosmology.
Right, the story definitely doesn't end with relativity. In fact, it just gets deeper.
How does the tensor formulation clean up the original 4 Maxwell equations?
Amazingly well. Remember, Heaviside gave us 4 vector equations. Using the field tensor, those 4 collapse into just 2 tensor equations.
2, down from 20, then 4, now 2.
Yep. The first one combines Gauss's law for electricity and the Ampere-Maxwell law. It relates the field to its sources, the charges and currents.
Okay, that covers how fields are created. What's the second one?
The second equation combines Gauss's law for magnetism, no magnetic monopoles, and Faraday's law of induction. It describes the field's inherent structure, essentially. Partial mu to Solica way. That tilde over the F means we're using the dual tensor, where E and B roles are kind of swapped.
So all of classical electromagnetism in 2 lines, that's elegance. But you mentioned something about that second equation, the source-free one, being almost automatic.
Yes. This is subtle but profound. The second equation, partial mu tilde dollars, which represents no magnetic monopoles, and Faraday's law, isn't really an independent physical input in the same way the first one is. It turns out that if you define the field tensor in the standard way from the underlying 4-vector potential mu, specifically partial anu partial mu, then that second equation is automatically satisfied mathematically. It's a built-in consequence of expressing the fields in terms of potentials.
It's called the Bianchi identity.
That's the one. It's a geometric identity. It means that the lack of magnetic monopoles and the existence of electromagnetic induction aren't separate empirical facts we have to add in. They are consequences of the very mathematical structure, the potential formulation of the electromagnetic field. The geometry dictates that part of the physics.
That's deep. And this inherent perfection is why Maxwell's work survived the quantum upheaval.
It's absolutely central to it. Think about it. Newton's laws, replaced by quantum mechanics. Newton's gravity, replaced by general relativity. Maxwell's equations, they sail right through the quantum revolution and land smack dab in the middle of quantum electrodynamics, QED, our quantum theory of light and matter.
They didn't need to be fundamentally changed.
Nope. The classical Maxwell equations become the operator equations of motion for the quantum electromagnetic field in QED. It's the only classical field theory to achieve this. It was somehow already quantum ready.
It became the blueprint for quantum fields.
The absolute prototype. All the other quantum field theories for the strong and weak nuclear forces are built using the same fundamental principles and mathematical structures pioneered by Maxwell's theory, especially the concept of gauge symmetry.
Okay, gauge symmetry. We talked about potentials, AMU being maybe more fundamental than E and B. Why are they essential for QED?
Because QED is built on a principle called gauge invariance. This is kind of redundancy in the description.
Yeah.
You can change the potential AMU in a specific mathematical way, a gauge transformation, without changing the physical E and D fields at all.
Why is that redundancy important?
It's incredibly important. In quantum field theory, demanding that the theory respects this gauge symmetry forces the carrier particle of the force, in this case, the photon, to be massless. It also dictates the form of the interaction between light and matter. You simply cannot build QED consistently without using the potentials of Magnetism and enforcing gauge symmetry.
So Maxwell's original focus on potentials, which Heaviside sort of streamlined away, turned out to be the crucial link to the quantum world.
Absolutely. History came full circle on that one. The deeper potential-based view was the quantum correct one all along.
Incredible. Okay, one last piece of the legacy. Tracking energy and momentum in the field itself.
Right. The field isn't just a mathematical tool. It carries real energy and momentum. And the way we account for that is using another tensor, the energy-momentum tensor.
Another 4x4 grid.
Yep. And this one is built directly from the field tensor. Its components tell you everything about the energy dynamics of the field.
Like what specifically?
The θ component, top left, is the energy density, how much energy per unit volume is stored in the field. The T components, rest of the top row, give you the energy flux, how much energy is flowing in direction, I dollar. That's the pointing vector, basically.
Okay, energy density and flow. What about momentum?
The T components, first column, give you the momentum density of the field. And the remaining TAG block, the spatial part, represents the stresses and pressures exerted by the field, often called the Maxwell stress tensor.
So energy, momentum, flow, pressure, all packaged together.
All in one object. And the killer app is its conservation law. In empty space, where there are no charges or currents to exchange energy with, this tensor obeys partial mu.
Which looks like the charge conservation equation.
Same form.
Yeah.
And it packs a double punch. If you look at the mu dollar component of this equation, it expresses the conservation of energy. If you look at the nu dollar 233 components, it expresses the conservation of momentum in each direction.
One equation covers both conservation laws, unified relativistically.
That's the power of the tensor formulation. And this isn't just for EM. This energy-momentum tensor is the object that tells space-time how to curve in Einstein's general relativity. This is the source term for gravity.
So Maxwell's description of field energy directly plugs into our best theory of gravity. The connections just keep spreading.
It's hard to overstate his impact. When you sum it all up, Maxwell didn't just solve a few problems. He shifted paradigms. He brought probability into the core of physics with statistical mechanics. He achieved the stunning unification of electricity, magnetism, and light.
And maybe most profoundly, he built the mathematical structure, the relativistic field theory, using potentials and tensors that was perfectly poised for the revolutions of the 20th century. It anticipated relativity and formed the bedrock for quantum field theory.
He delivered the blueprint. And that blueprint has one final amazing feature revealed by that energy-momentum tensor that connects directly to the universe itself.
Okay, the final provocative thought. What's the secret in
The determinant for Maxwell's electromagnetic field has a unique property. It's traceless. The trace is the sum of the diagonal elements. For electromagnetism, that sum is 0, plus T11 plus T22 plus T3 $.
traceless? What does that imply physically?
Mathematically, it's related to something called conformal symmetry. Physically, it's characteristic of a field whose quantas are massless like the photon. A traceless energy-momentum tensor imposes a specific relationship between the pressure the field exerts and the energy density it contains.
And how does that connect to cosmology?
When we modeled the very early universe using Einstein's equations, the Friedmann equations, the universe was so hot it was basically filled with a gas of pure radiation photons. We need to know the relationship between the pressure and energy density of this photon gas to see how the universe expanded.
And Maxwell's traceless tensor tells us that relationship.
It dictates it. Because the electromagnetic field representing the photons has a traceless tenue, the pressure of that primordial photon gas must be exactly 1/3 of its energy density. T equals C 3 to 5.
That specific fraction, 1/3, comes from Maxwell's classical equations.
It comes from the traceless nature of his energy-momentum tensor. That pi parallel is E33 equation of state is what governs the expansion of the universe during its early radiation-dominated era.
So Maxwell's 19th century classical equations contain the key property needed to understand the expansion of the entire cosmos shortly after the Big Bang.
It's just astonishing, from statistics of gases to the nature of light to the structure of space-time to the quantum world and finally to the evolution of the universe itself. Maxwell laid down foundations that physics is still building on today. A truly unparalleled legacy.